I want to take the derivative of e to the x. And I'm going to do so by using the definition of derivative. I'm going to do it that way because I don't know a rule for e to the x yet. I have a rule for x raised to a constant, the power rule. This is a constant raised to the x. So I have to use the limit definition of derivative, which means I need to simplify this difference quotient. And I see a few things I could go on and do. But what I'd like to do first is remind you what the number e is. In your textbook, there's a derivation or a definition of the number e using only concepts from our calculus course. But I thought what we could do together in this video is remind ourselves of where we probably saw e for the first time in an algebra course. For a lot of students, e is first introduced as a consequence of the compound interest formula, that e can be used in that specific application. So I'm going to start in that application and then end up with a definition of e that's completely in terms of a limit that I can use to find the derivative of e to the x. So here I have my compound interest formula. The balance A is equal to the principal P, that original amount of money, times 1 plus an annual interest rate divided by the number of times interest is assessed in a year, raised to the n times t, where t is the number of years. Well, I understand what happens if I put in more or less money. I understand what happens if the interest rate is higher or lower. And I understand what happens if t keeps going on, if the number of years increases. So the only thing I have any curiosity about is what happens when n changes. So I'm going to imagine that I plug in 1 for p, that I've put $1 in an interest account. For simplicity's sake, I'm going to let the interest rate be 100%. That's never going to happen in life, but if I found an investment account with an interest rate of 100%, I would definitely take it. And I'm going to imagine that t is also 1, that I do this for 1 year. So I end up with this equation. Well, if n is equal to 1, I have 1 plus 1 raised to the first power is 2, and that makes sense. If I earn interest one time in 1 year and the money is always at doubling because the interest rate's 100%, I'll end up with $2. So what I've done is I've set up my graphing calculator so that I can look at what happens when n gets really, really big. So in my graphing calculator, I just plugged in this formula, but I used x instead of n because my calculator is not set up to understand what an n is. And I'm just going to use the table to plug in higher and higher values for n. When n is 1, I get out of 2. If I earn interest twice in a year, the y value has now gone up to 2 1/4. That quarterly compounded interest, 2.44. So right now what I see when n is increasing, the y value also looks like it's increasing. I want to continue just letting n get bigger. Annual interest, interest every day in a year. And now I just want to think in terms of letting n get bigger. I don't even have to think about the application of interest anymore. Let's say I have n is 1,000. And I see that the y value got bigger, but what I notice is it's not always getting bigger by the same amount. In fact, it looks like it's getting bigger by smaller and smaller amounts. And so now I'm thinking that my y values are leveling off. In our language, in the calculus course, n is going to infinity, and I think my graph's approaching a horizontal asymptote. Let's see, I plugged in 10,000, so let's plug in 100,000. And then 1,000,000. And what I see is, I think, that was another 10,000, not 100,000. Let's see if I can do that correctly. Counting is hard. All right, and what I see is I got the same number twice. Now, what I'm going to say is that as n goes to infinity, this expression seems to be going towards a number, and I want to call that number e. And I could actually use this to define the number e. And then e is about 2.71828 ... E is an irrational number. It's like pi. Its decimal approximation never terminates and it never repeats itself. This could be my definition of the number e. E is simply the number that this limit approaches. Okay, that doesn't help me as much maybe in this problem as I want it to, because this has a limit as h is tending to 0. This has a limit that's going to infinity. So I'm going to do a little variable swap by being creative to define e using a limit that's approaching 0 instead of infinity. I'm going to replace n with 1 over h. One thing I have to be careful about is in my bad handwriting, the n's and h's sometimes look alike, but n is equal to 1 over h. And if I think about that, that means h is also 1 over n. So, if n goes to infinity, I want to think about what's happening to h. Well, h is the reciprocal of n. If n goes to infinity, the bottom of this fraction is going to infinity. The top's always 1, that's going to 0. So when n goes to infinity, h tends towards 0. So I can rewrite that limit, instead of as n goes to infinity, as an h goes to 0. Just by replacing n with 1 over h. 1 plus, well, 1 over n is h, and n is 1 over h. So this limit, now in terms of a variable going to 0, is also a definition for the number e. So anytime I see the number e, I could replace it with this limit, or anytime I saw this limit, I could replace it with the number e. For us, what I'm getting ready to do is I'm going to see an e, and I'm going to replace it with this limit. All right, so I'm going to make a note of that. That if I have the number e, I could think of that as a limit as h tending to 0 of 1 plus h to the 1 over h. Now let's see what I can do with this difference quotient. I have a limit as h is going to 0 of e to the x plus h. I'm going to rewrite that as e to the x times e to the h minus e to the x all over h. This works because when I'm multiplying things with the same base, I add their exponents. So I can rewrite it like that, and what I see now is I can factor out an e to the x. All right, and what I realize is this no longer has an h in it, so in terms of this limit, whose variable is h, I can pull that out front using my limit laws. All right, and this is where I'm going to use this statement. I have a limit as h tends to 0, so I'm going to rewrite the number e as this expression. And I'm really thinking about my limit laws, right? That I could break all of this apart to where I was just taking the limit of that e to the h. Because h is tending to 0, I can replace that e with 1 plus h to the 1 over h. And e was itself being raised to the h power minus 1. H is going to 0, which means the thing in this bracket is going to 0, which means that is the number e. I have a 1 over h to the h. When I raise a power to a power, I multiply, so those cancel, and I just get 1. All right, so I'm going to transfer that to the next board. And we've almost found the derivative of e to the x. So I had a 1 plus h to the 1 over h to the h. So those, in effect, canceled because h times 1 over h is 1. Minus 1 all over h equals e to the x times that, right? That's the limit I was working with. All right, on top there, I have 1 plus h minus 1. Which will give me an h over h, which is always 1. The limit of a constant is that constant, so I have e to the x times 1 is e to the x. I found the derivative of e to the x. The derivative of e to the x is e to the x. It's a very special function whose derivative is itself. This is super cool. In terms of an application, if something is growing exponentially, its instantaneous rate of change is also growing exponentially. All right, let's put that together with a couple other rules we know. That's what I always want to do in these videos at the end. Find y prime. y is equal to 2e to the x plus 3x to the third minus 4x squared plus 5 million. All right, y prime. Well, the derivative of e to the x is e to the x. The constant multiple rule says I would just double that. Plus 9x squared minus 8x, and the derivative of a constant is always 0. There's my nice, happy derivative.